Welcome back to Calculus 1. I'm Dr. Jeff Groh, and this is your Calculus Exam 1 Review. Problem 1. What is the limit as x goes to infinity of 13x cubed minus 3x squared plus 3x plus 1 all over 23x cubed plus 12x squared plus 13x minus 9. On this problem, x is getting big, and in the case of a rational function, if the degrees are the same, then the answer is the ratio of the leading coefficients. So the answer is 13/23. Problem 2. Find the limit as x goes to 9 from the left of the absolute value of x minus 9 over x minus 9. This function has the following graph. To the left of 9, it has a height of -1. To the right of 9, it outputs a height of 1. Since we're approaching from the left, the answer is -1. On number 3, we have the limit as x goes to 0 of 1 minus cosine x over tangent of x. There are a number of ways of approaching this. I think an easy one is to do the following. We'll take the limit as x goes to 0 of 1 minus cosine x over x times x over tan x. From the work that we've done earlier in this section, we know that x over tan x, and in particular tan x over x is what we saw earlier, tends to 1, whereas 1 minus cosine x over x tends to 0. So the answer is 0. But let's try to prove this in a different way. If you didn't like the last approach, here's another one. Why not multiply by 1 plus cosine x over 1 plus cosine x? The numerator foils and becomes a difference of squares, 1 minus cosine squared x. You'll have 1, a positive cosine, and then a minus cosine, and then a minus cosine squared x. In the bottom, let's rewrite this as sine x over cosine x times 1 plus cosine x. Now, by the Pythagorean identity, 1 minus cosine squared x is sine squared x. Fractions, when you divide them, you invert and multiply. Inverting and multiplying, we're going to have a cosine x divided by sine x. When you flop this up, it's going to cancel one of these signs. The only thing left in the denominator will be the 1 plus cosine x. Now, as x goes to 0, cosine x goes to 1. 1 plus 1 is 2. We have a factor of 1 in the numerator, but sine of 0 is 0. The whole thing is 0. On problem number 4, we have the limit as x goes to minus infinity of 11x cubed minus 3x squared plus 3x plus 1 over 17x squared plus 13x minus 9. On this problem, since the degree in the numerator is higher than the degree in the denominator, the limit is either going to be plus or minus infinity. We need to figure out which one. Since we're going to minus infinity, a negative large number cubed is still negative, and it's multiplied by a positive 11, so that ends up being a negative large number. In the denominator, since we have a square, we'll have a positive large number, but not as large as above. So the answer is minus infinity. In problem 5, we have the limit as x goes to minus infinity of the absolute value of x minus 1 over x minus 1. This function has the graph that outputs negative 1 for values less than 1, and to the right of 1 it outputs heights equal to 1. As we go to minus infinity on the x, the y values are always minus 1, so the limit is minus 1. On problem number 6, we have the limit as x goes to 3 of x cubed minus 27 over x minus 3. There are a couple ways that you can approach the solution to this problem. One way is by long division. You can actually divide x minus 3 into x cubed minus 27. Another way is by just knowing how to factor a difference of cubes. X cubed minus a cubed is x minus a times x squared plus ax plus a squared. In this case, that would give us the limit as x goes to 3 of x squared plus 3x plus 9. When x goes to 3 now, we get 9 plus 9 plus 9, and the answer is 27. We could have done this by synthetic division as well. The coefficients in the numerator are 1, 0, 0, negative 27. The root of the denominator is 3. You always carry the leading coefficient down and then multiply and add. Multiply and add. Multiply and add. You see that this goes in evenly since there's no remainder. What's left are the coefficients of the polynomial in the division. 1x squared plus 3x plus 9. And then you get 27. On problem 7, we have the limit as x goes to 7 from the right. Absolute value x minus 7 over x minus 7. Of course, the graph has a jump discontinuity at 7, taking on values of minus 1 to the left and positive 1 to the right. Since we're approaching 7 from the right and the values are all 1 there, the limit is 1. On problem 8, we have the limit as x goes to 0 of the tangent of psi x divided by omega x. As you know, the answer should be psi over omega. Don't give too much credence to all these Greek letters. We can treat them as roughly and arbitrarily as we wish. One way to approach the solution to this problem is to write this as the limit as x goes to 0. We'll put the omega out here and a psi and rewrite this as the tangent of psi x over psi x. If we replace psi x with y, we can rewrite this then as the limit as y goes to 0 of psi over omega of the tangent of y over y, which we know tends to 1, and hence the answer is psi over omega. On our next problem, we have the limit as x goes to positive infinity. I don't think I wrote the positive, but you may interpret it that way. Negative 4x to the fourth plus 3x plus 1 all over 12x cubed plus 12x squared plus 13x minus 9. Only the leading terms matter, and since the degree in the numerator is higher than the degree in the denominator, this will go to plus or minus infinity. We just have to figure out which. Since we have a negative coefficient here and a positive coefficient on the x cubed, the answer will be minus infinity. On problem 10, we have the limit as x goes to infinity of the absolute value of x minus 5 over x minus 5. It helps to know what this function looks like. Negative 1 until you get 5, and positive 1 after. So if you're going to infinity, all of these values are 1. The limit is 1. Problem number 11 has the limit as x goes to 3, the absolute value of x minus 3 over x minus 3. This function also has a jump discontinuity, this time at 3, but we're taking the limit as x goes to 3, which means from both sides. On the left we have a limit of minus 1. On the right we have a limit of positive 1, which means this limit does not exist. On problem 12, we have the limit as x goes to infinity of cosine x over x. The limit is 0. Now, why is that? You can think of it this way. Cosine is trapped between negative 1 and 1. We're only interested in taking the limit as x goes to positive infinity. So if we divide by x, we'll divide by x's on the domain with positive x values. That won't change the direction of any of these inequalities. Now, using the Squeeze theorem, the limit as x goes to infinity of negative 1 over x is obviously 0. And that too is the limit as x goes to infinity of 1 over x. So the functions on left and right are being sent to 0, which means the one in the middle is sent to 0 as well. Another way to think about this is that cosine is always trapped between negative 1 and 1, but the bottom is blowing up, and everyone knows that 1 over huge is tiny. Problem 13 is a problem that students often struggle with. It's the limit as x goes to minus infinity of 4x cubed minus 7 over 2x cubed minus the square root of 36x to the 6th power plus 1. Now, as x gets big, this plus 1 won't really matter. So we can actually ignore this. We can also ignore the minus 7. One way to see that is to just multiply top and bottom by 1 over x cubed. If we do that, we have the limit as x goes to minus infinity of 4 minus 7 over x cubed, which goes to 0, over 2 minus, now we have this 1 over x cubed here. We have 36x to the 6th plus 1. There's a little technicality that helps in understanding the solution to this problem. Here's what we'll do. We'll factor x to the sixth out. And when you take the square root of x to the sixth power, what do you get? You don't get x cubed. You get the absolute value of x cubed, because the radical symbol is not any square root, it's the principal square root. So we end up with the absolute value of x cubed over x cubed times the square root of 36 plus 1 over x to the sixth. This last term goes to 0. Square root of 36 is 6. But what happens in the limit as x goes to minus infinity of the absolute value of x cubed divided by x cubed, just this factor? Well, absolute value turns things positive. So the top will be positive and the bottom negative. But having the same magnitude, the ratio will be -1. We'll have 2 minus 1 times 6, all underneath the 4. Going the wrong way on the board, then, the answer is going to be 4 over 2 minus -1 times 6. Minus minus is plus. We have then 4/8, or 1/2. On problem 14, we have a limit of a difference quotient. The limit as h goes to 0 of the square root of x plus h minus the square root of x all over h. This is one of those classics where you need to multiply numerator and denominator by the conjugate of the numerator. Root x plus h plus root x over root x plus h plus root x. Since I'm multiplying both top and bottom by the same value, I'm not changing the value of the expression, only its form. This gives me the limit as h goes to 0. When I FOIL out the numerator, I'll have x plus h. We'll have root x times root x plus h, and then minus root x times root x plus h, which cancels out. And then we have minus x. We still have h times the square root of x plus h plus the square root of x. The x's in the numerator cancel out. That leaves just an h, which we can cancel with the h in the denominator, leaving only a 1 in the numerator. We'll now take the limit as h goes to 0, and we'll get 1 over the square root of x plus the square root of x, which is 2 times the square root of x. Problem number 15 asks where the function f of x equals x minus 4, x minus, is that a 5, x minus 2, over x plus 3, x minus 7, and x plus 12. Sorry for the confusion on that middle one, but just a bad printout. This is a rational function, and rational functions are continuous everywhere except where you get division by 0, everywhere except where you can make the denominator equal to 0. So this is continuous on the entire line except for minus 3, 7, and minus 12. On problem 16, we're asked to find the x values where the following function is continuous, and to justify our answer. This function is 0 on all irrationals and looks like y equals x on the rationals. There's only one point where this can be continuous. So note that the limit at any a not 0 the limit as x goes to a of this function does not exist. Therefore, f is not continuous if this a is not 0. What happens at x equals 0? At a equals 0? If a is equal to 0, the limit as x goes to 0 of f of x is 0. What about f of 0? 0 is a rational number, and you output just whatever you input if the input is a rational number. So the answer is 0, which is the limiting value. Since the limit exists and the function value is defined and the limit value equals the function value, we deduce that this function is continuous at x equals 0. And only at x equals 0. And we have fully justified these answers. On problem 17, we're asked to prove that the function f of x is equal to 2x cubed plus 3x squared plus 4x minus 1 has a 0 between 0 and 1, somewhere on the interval 0 and 1. Here's our proof. First, note that f is continuous since it is a polynomial. Where is it continuous? On the entire real line. Also, f at the left-hand endpoint is minus 1, and that's negative. F at 1, the right-hand endpoint, is 2, plus 3 is 5, plus 4 is 9, minus 1 is 8. And that's positive. 0 is intermediate to the negative 1 and the 8. So, by the intermediate value theorem, there must exist some point C between 0 and 1 such that the height at C is 0. And that's the end of the proof. On problem 18, you are asked what three conditions must be met for a function to be continuous at x equals a. The answer: 1. The limit as x goes to a of f of x exists. 2. F of a is defined. And 3. The limit as x goes to a of f of x equals f of a. On problem 19, I asked that you prove that the limit as x goes to 2 of 3x minus 5 equals 1 using the definition of the limit, i.e. epsilons and deltas, the epsilontics. So here's our proof. Let epsilon greater than 0 be given. We want epsilon to be greater than 3x minus 5 minus 1, which is the absolute value of 3x minus 6. which is 3 times the absolute value of x minus 2. And that happens if and only if the absolute value of x minus 2 is less than epsilon divided by 3. At this point, we can see that we want to set delta equal to epsilon divided by 3. When this is true, whenever 0 is less than the absolute value of x minus 2 is less than delta, which is epsilon divided by 3, then we get what we need. The absolute value of 3x minus 5 minus 1 is less than epsilon. And that's the end. We're down to the last page and the last problem on the practice exam. Problem number 20. I ask about the following function, f of x equals 3 minus x when x is less than 0, 3 plus x squared when 0 is less than or equal to x is less than or equal to 1, and 2 minus x when x is greater than 1. I ask, where is the following function continuous? Use the definition to prove your answers at x equals 0, at x equals 1. So in our answer, we'll say f is continuous everywhere except 0 and 1, because everywhere else it's a polynomial. Polynomial on each interval. The only question that remains is, let's try x equals 0 first. We'll take the limit as x goes to 0 from the left. On the left of 0, we use 3 minus x. Well, that limit is 3. What happens if we take the limit as x goes to 0 on the right? To the right of 0, you have to use 3 plus x squared. That limit is also 3. Since the limit on the left equals the limit on the right, the limit as x goes to 0 of this function will be 3. What is f of 0? X equals 0 uses the middle, 3 plus 0 squared, which is 3. That's equal to the limit value, therefore f is continuous at x equals 0. We still have to check continuity at x equals 1. At x equals 1, when we take the limit as x goes to 1 from the left, to the left of 1, we use 3 plus x squared. As x goes to 1, we get 4. Take the limit as x goes to 1 from the right. To the right of 1, we have to use 2 minus x, which gives 1. These limits are not equal. Therefore, the limit as x goes to 1 of f of x does not exist, and f is not continuous at x equals 1. But to answer this question, we have to state where this function is continuous. F is continuous on the entire real line except at 1.